to hit record. All right, we are now recording. So again, chapter 2 is vectors in space. Chapter 2, section 1 is vectors in the plane. We can all probably assume why the satellites are our image under the intro. Okay, so vectors. Hopefully vectors are not a brand new thing to you guys. I mean, I'm assuming at Calc 3, I'm not sure what physics class coincides with Calc 3, but vectors at this point should not be too scary. Hopefully it's a little bit of a review and not just a brand new thing. But if it is brand new, we have our initial point and we have our terminal point. Of course, your initial point is actually a point and the terminal just continues forever in the direction in which case the segment is going. Going to obviously let you guys read that for yourselves there. Why do you think vectors 1 through 5 are equivalent?
They have the same direction and magnitude.
There you go. Yeah. So, I mean, it doesn't really matter what we sub anything, as long as they're all facing that same direction and you can all see that they continue forever. It's not like one of them is stopping 5 units in or 3 units in. They are all continuing forever in that same general direction. Okay. I'm going to assume that unless someone stops me that I can move kind of at my own pacing. All right. So this next figure, we do have some points of reference. So we have line PQ or vector PQ, and it's starting at point P, which is at 1, 1, and going towards and through technically Q, which is 8, 5. What I do find interesting about that is that really it's not stopping at 8, 5. So please don't think that it is. They're just wanting to name it something other than singular vector, so they picked another point. Also, you guys will notice that, and this is something that I'm going to try to fix, the PowerPoints are very ridiculous in that, so it showed us this figure, right? And it gave us this information. And that's all it did. And we were supposed to glean something from that. So this is actually the example that goes along with it. It actually wanted you to sketch a vector in a plane. And for some reason, in the PowerPoint, I promise you that was all that was currently given. I added this. So I guess it should have gone in front. I was trying to figure it out. It got a little jumbled. So yes, if you were asked to sketch a vector in the plane from the initial point to the terminal point, I'm hoping that at this point, if that was on your test and we replaced P with R and R was 2, 5 and the terminal point was S and it was 13, 10, all of you guys should be able to handle that. Okay. Any questions on sketching vectors? Okay. All right. I agree. Thumbs up. Okay, so for anyone who needs to write down definitions, that was the other thing. The PowerPoints had no definitions. This is why I tell you guys to try to use them in concert. I will try to pull everything that I see, but if I miss something, make sure you write it down. All right, so the product KV of a vector V and a scalar K is a vector with a magnitude that is K times the magnitude of V with the direction that is the same as the direction of V if K is greater than 0, and opposite direction if K is less than 0. This is called a scalar multiplication. If K is 0 or V is 0, then KV is also 0. Kind of all intuitive there, right? Okay, so guys should be good to go on that, but if anyone would like to write it down, I will give you the time to do so. Okay. And then the really cool thing about it being recorded is that if I ever do go too fast, you can always pause me, which I think is just the funniest thing to say. I don't know, it still cracks me up at like after so many years of doing stuff on Zoom. Okay, so the original vector v has length n units. The length of 2v equals 2 times n units. The length of v over 2 then is obviously n divided by 2. And the vectors v and negative v have the same length but opposite directions. So that's just kind of showing you the different types of things you can do with vectors. I'm sure you guys could replicate this if, if the test problem had just the wordings. I'm sure you guys could all write this out. The nice part is that I'm not going to sit and hold a ruler up to your test paper. I'm just going to see that if it is labeled correctly and that you kind of don't draw the same exact length vector, it's going to be good enough for me. Okay. Does anyone have any questions on those or disagreements? Hopefully you don't have any disagreements. They are all there. Okay. So here's another definition. The sum of two vectors v and w can be constructed graphically by placing the initial point of w at the terminal point of v. Then the vector sum v plus w is the vector with the initial point that coincides with the initial point of v and has a terminal point that coincides with the terminal point of w. This operation is known as vector addition. Isn't it really amusing that the farther we go in mathematics, the lower we go in mathematics at the same time? Like when they tell us that everything builds, you really don't get that full picture until you continue going on in mathematics and realize, oh, if I really didn't understand the concept of addition, when I was 5, it still keeps coming back around. So, all right. So for vector addition, it's gonna remind you probably of Pythagorean theorem a little bit. At least it does to me. You're pretty much drawing some triangles there. When adding vectors by the triangle method, the initial point of W is the terminal point of V. And then you can also use the parallelogram method. The vectors V and W have the same initial point. It's going to get you the same answer no matter which approach you use, so dealer's choice. Okay. Alrighty. The vector difference v minus w is depicted by drawing a vector from the terminal point of w to the terminal point of v. The vector v minus w is equivalent to the vector v plus the opposite of w. Okay. Same general statement there as well. You can see everything kind of written out. And this is just the first day stuff, so it will get harder, right? Vectors v and w lie in the same plane. Not really sure why we have, I think it might go with another problem. It's probably showing us the answers first. So we also have 3w and w. You can see that relatively speaking, w is a third of 3w. Again, as long as you kind of make the length, you don't have to sit there and draw it with a ruler. You may certainly do so, but I'm just letting you know that I'm not going to be grading anything using rulers. So, to find W plus or V plus W, align the vectors at their initial points or place of the initial point of one vector at the terminal point of the other. And then you can see that A is showing that vector V plus W is the diagonal of the parallelogram with sides V and W, and that B is the vector V plus W is the third side of the triangle formed with W placed at the terminal point of V. Again, you get the same answers. Not quite sure why we're hammering it so hard here, but all right. And then to find 2V minus W, simply add 2V plus the opposite of W. So if W would have been going this direction, then you just flop it over. All right. I think the definitions get easier to understand when you do the homeworks, and you can see it more and be able to actually use it and do it instead of just wondering why they have the examples they have. All right, somebody other than Tiffany, because she answered the first question. Why are these vectors not equivalent? It's telling us, but why? All right, we have an answer in the chat. Oh no, I just moved all of you. All right, so, yep, pretty easy to see there. We have different directions, so V is going off to the right, and W is going up to the sky. Sure, up towards Y. So we have one going in the positive X and one going towards positive Y. All right, and they were obviously nice and gave it to you in different colors. So that is cool. All right, and then again, we know that these ones are equivalent, even though they're trying to trick you and give it to you in different colors. If you literally moved V up towards W, you would see that they would fall on each other, going in the same directional, so they are equivalent. Okay. All right, and then again, I think they had a question on that one, but I believe basically the question was if any of them are equivalent. It doesn't. It doesn't appear like it looks like the only ones that might be would be B and E potentially, but it could be my screen too. So I would just check that one out in your textbook to get what they were fully after there. All right, definition. The vector with initial point 0, 0 and terminal point xy can be written in a component form as V equals xy. The scalars x and y are called the components of V. Okay, should not be scary to you guys at this point. Wait until they are trigonometric functions, and then you could get a little bit scared. All right. Rule component form of a vector, let V be a vector with the initial point x sub I, y sub I, and the terminal point x sub t, y sub t. Then we can express V in the component form of V equals, there you go, right? So again, if you're someone who takes down notes, I would obviously write it down, but you're probably going to get more out of just doing the homework. Okay. And as I said before, I will try to squeeze homework in going forward. If nothing else, we might start the day with homework questions that you might have, and then go into the lessons. Right. I will also apologize to you guys. I'm a very fast presenter. I don't know why, but it ends up helping you guys out in the end because number one, you can watch the recordings at your own pacing, and number two, it lets us have more time to do work. So it does end up helping in the end. So these vectors are equivalent. I find it slightly amusing that they didn't name their vectors differently. They probably got a little lazy and literally just copied and pasted, and they didn't want to change their V to something else. So if you didn't think it was the same, they literally labeled it the same as well. So, and you guys can see why it is the same. Okay. So as long as we have the same directional and the same units going on, it does not matter where you move the arrows to or the vectors to, it's going to be equivalent. So I thought this was neat. They had it in the textbook. So in the textbook, they obviously showed this part first. And again, they just don't like to give you the question. I am going to have to fix that going forward. Luckily, these questions are kind of easier, so we can kind of connect with what they wanted to say, but I'll make sure all the questions are up. So they also did it from an algebraic standpoint too, which I personally love algebra. So if you want to answer some of your calc questions using algebra, I don't have a problem with it as long as you get the same answer in the end, which you should if you know your algebra. But also if you feel like you would like to do it with their geographical technique and their algebraic, I may or may not be willing to give some bonus points for that on exams, so just keep that in mind. All right, so in the first solution, we used a sketch of the vector to see the terminal point lies 4 units to the right. We can accomplish this algebraically by finding the difference of the x coordinates. Similarly, the difference of the y coordinates show the length, vertical length of the vector. So then in component form, we would have v is equal to 4 minus 2. And if you go back to that graph, whoops, stop. You can see that you have a positive 4 and a negative 2. Okay. I personally probably would have done both. I would have sketched my graph and then I would have worked out the algebra, mainly because I probably wouldn't have realized that my graph was enough work. Okay. If you use the components of a vector to define a right triangle, the magnitude of the vector is the length of the vector of the triangle's hypotenuse. Okay. Again, that's why the other slide reminded me so much of Pythagorean theorem. Just so I'm kind of aware on it, I have taught at a lot of different schools. So is this review from Calc 2? Or is this just review in general, or is it new stuff? Okay, cool. All right, neat. All right. I had a feeling that was going to be the case. All right. Okay, so let V equal, you guys can see it in W, be vectors and K be the scalar. So then scalar multiplication, you can see how it works out, vector addition. And then performing operations in component form. Again, I don't think I can stress how much your basic, like your basic math comes back into play. Which, like I said, it's just amusing to me. So, and then I think it does show it. Okay, cool. So, and like I said, now that I definitely know that it's review, we're just gonna kind of just check everything out. So here's our component form. V is equal to 6, 8, which would obviously be shown both of those there. Okay. And then I'm not gonna talk all of this out to you guys. You can clearly follow along and see that is there. So V is equal to 8 minus 2, and then 13 minus 5. So again, we have 6, 8. And then you have your magnitude, which is 10. And then V plus W. So 6, 8 plus minus 2, 4. We get 4, 12. Right? So that's A and B. And then here is C and D. 3V. 3 times 6, 8 is going to give us 18, 24. And then V minus 2W is going to give us 10, 0 at the very end. Right? Again, since you guys said that was all review, hopefully you wouldn't have any trouble following that stuff. Just in case anyone is like a crazy, I'm not going to say crazy, I guess a prolific note taker. I am a prolific lister. I love listing things and crossing them off. It's like one of my most favorite things to do. I've even made lists for my Pokemon games. Like I have intense Excel files for my Pokemon games. So anyway, if you're someone who would at some point, if we have time, I'll anyone who's interested, I'll show you them. But if you would like the basic capped version of our properties, they're here for you, obviously using vectors and not your basic numbers. But also feel free, if you're more of a computer person, if you just want to screenshot certain things, or you can do that once you get the PowerPoints. Really kind of fine with however you guys choose to do your notes, as long as come the first test time, you're all good. Yes. Yes, I am a massive gamer. Hoping to start a YouTube channel at some point, which I think would just be amusing, since my original YouTube channel had to get used during COVID for teaching. So now I have to get a new one. All right. Proof of community commutative property and proof of distributed property. And then it also has a checkpoint there that I added for the additive inverse property. I will say that even though these are a little I guess we'll say not really juvenile, but lower leveled, you would be surprised the like mental workout you get trying, like going through and doing some of these proofs. I guess as a side note for proofs, I will tell you that in grad school I took abstract algebra and real analysis. I mean, I've taken a lot of classes, but I feel like those two in particular, I got an A in them, and a lot of my friends who hadn't taken that class yet were like, how did you do that? And honestly, my answer was I just wrote the proofs constantly over and over and over and over again. I can't tell you, like, really to this day what some of those proofs even mean, but thankfully we don't have to teach real analysis or abstract, so but yeah, proofs are definitely where some of you may have to put in some time. But calculus, for the most part, does not have too many proofs. I guess not too many proofs like that. All right, the components of a vector form the legs of the right triangle with the vector as the hypotenuse. They have told us this before. Here you just see the difference of their now bringing in sine and cosine. So using trigonometric ratios, x is equal to the magnitude cosine theta and y is equal to the magnitude of v sine theta to identify the components of the vector. Okay, again, that should be review from trig, kind of, but also, I guess, calc 1 and 2. All right. Again, we didn't have our question first. Okay. So let x and y represent the components of the figure. Then x is obvious. So they just went through and they actually did the problem for you. Okay. If you haven't already done the homework, I'm gonna guess it's gonna be pretty much on the same realm of just reviewing for you. That's another reason why I went ahead and did this one today. Hopefully the whole chapter won't be review, but I guess if it is, kind of gives you guys a nice first test. The vector v and the associated vector u, in this case, the magnitude of v is greater than 1. Okay. All right. Okay. If anyone wants to write that down, honestly, we only have a few more slides left. I would just, I would probably just check that part out in the textbook if you want the whole view there. I am aware of how crappy the PowerPoints are. We're gonna make them a bit better for the harder sections. I don't think it's terrible for a review section to have it like this, but the harder stuff, we're definitely gonna want those actual questions. This is what happens when you let the publishers take their credit. So the standard unit vectors I and j. As you guys continue on with higher maths, you will find that you will see those everywhere. So I guess just get used to them now if you haven't already. Okay. All right, the vector v is the sum of x, I, and yj. I feel like this is a review within a review. They've shown us this stuff a few times, right? The terminal point of view lies on the unit circle, can be found using cosine theta, sine theta. So that can get a little trippy if you look at that too long. So I don't recommend that. Okay. And so I guess before I forget, it was in the syllabus, but I am supposed to announce it. I'm not sure how Calc 1 and 2 did it, if they changed it up or whatever, but Calc 3, I guess the work will not be so extremely difficult that you would need a graphing calculator, so they're only allowing for the scientific, and that includes on your test, or especially on your test. So if I were you guys, I would just get used to using that on your homework as well. And but I'm personally fine if you want to have a unit circle. I mean, you guys probably have more of the unit circle memorized at this point than I do. So if you would like to use a unit circle, I'm not going to tell you no. But I also don't know how much of it you'll actually need. So, did you guys have to memorize the unit circle? Probably at some point, right? Oh, okay. So we got some no's, we got some back in high schools, and we got some sure dids. Okay. Well, if you currently have it memorized, then feel free to continue. Should you want to be lazy, I'm fine. I will not be memorizing it again. I will just be using it because I will let you know this little secret. When you graduate and you get a job, I'm not sure if you're aware of this, but there's this invention called Google, and it comes with all of the resources that anyone could ever need or want. So that's my personal take on things. I try to teach from the real world perspective. So in the real world, I would not tell you that you can't have a unit circle. So you may certainly use the unit circle. But as I said, if you would like to continue root memorizing stuff that you then forget in 6 months, go for it. I'm not going to tell you no. All right, two forces acting on a car in different directions. So I guess if we wanted to think about this in real world situation, if we had really the vectors would be drawn differently, because probably more than likely we would have a tow truck pulling from the front or the top, and then probably something else going on in the back. But regardless, they're saying that we have two forces acting on this car in different directions. 150 pounds and 30 pounds with a 15-degree difference. To find the effect of combining the two forces, add their representative vectors. First, express each vector in the component form or in terms of standard unit vectors. I personally don't care how you approach some of these problems as long as you get the answer at the end of the day. So if you like it with one form versus the other form, whatever, I will say that I personally do much better when you guys are organized. So I've had students draw like boxes around like I don't know if any of your friends have taken Math 90 and you've seen the packets with like the square boxes for like problem 1 goes in the problem 1 box. I'm fine if you want to be that organized. I'm also fine if you just want to circle your answer. However you want to do it so that I'm not questioning where your answer is for what number. Is fine with me. So there you go. I guess our overall answer is the resultant force R has an angle of 5 degrees above the horizontal axis. Okay. So again, however you guys want to do for your stuff is fine with me. All right, we have another problem this time with a tin can that's flying probably way too fast. Initially, the plane travels due west. The wind is from the northeast, so it is blowing to the southwest. The angle between the plane's course and the wind is 45 degrees. Clearly, figures not drawn to scale. I will tell you the number one thing all of your physics professors should be telling you, and I'm sure they are, is going to be the same with your calc, which if you haven't figured it out at this point, if you can draw the situation, you should draw the situation. Okay? I'm a terrible artist, so even if you stick figure the situation, you should stick figure the situation. Okay? It will definitely come in handy if it hasn't already been proven to you. I'm sure it will at some point. So you want to set up your sketch so that the initial points of the vectors lie in the origin. I mean, that's just the easiest way. I would always, use that origin to your advantage. Then the plane's velocity is p equal to negative 425i. The vector describing the wind makes an angle of 225 degrees with positive x-axis. There you have it in vector form. Okay, so then your overall answer is the overall direction of the plane is 3.57 degrees south of west. Okay. All right, and do not leave yet, but I will say that this is what I'm telling you guys. When I saw 40 slides, I was like, oh man, that's going to take us forever. Let me go ahead and stop the recording.